talk, and I was reading through it. One of the objectives, and we actually had a workshop through NETL 2 weeks ago, which had a very similar kind of theme, was how all of the work we're doing in this community, how can it have significant impact within industry? Olivier mentioned in his talk that without predictive simulations, you can't do control or optimization. And I think that almost the majority of these talks, if you've noticed, has been focused on predictive capabilities. But predictions alone, we all understand, won't inform you how to improve a design. And so I think there needs to be simultaneous effort along with developing predictive capabilities. How do you quantify sensitivity? How do you quantify uncertainty? To leverage methods that are predictive. There does exist predictive methods in certain regimes, obviously not all of multiphase flows. How do we leverage that to inform reduced order models or improve a device? And I'm not going too much into that here. It's something that's been on my mind a lot. But here is, I guess, a little flavor of part of that. Most of this work has been done by most of this work has been done by my student Sarah. It's all very preliminary. We started looking at this 6 months ago, but it's been motivated by the past 4 years of research with Olivier Desjardins and Rodney Fox and myself. And I hope to kind of motivate that, as we go towards larger and larger scales, or as we go to this effort of reaching industrial scale, we need to start looking at new approaches that can both quantify, if we do a simulation at the particle scale and we trust that data, how do we reliably go to larger scales with quantified uncertainty, which I won't be talking about in this talk, but how do we do this in a robust manner that remains predictive? And I think this is a very large challenge, and that's one of the motivations for what I'll be showing. And so as one of the motivations, what I'm interested in is developing predictive models that remain tractable and robust across flow regimes. So this is showing a turbulent channel flow. All three of these cases have the same Reynolds number, and it shows how the budget of turbulent kinetic energy, the fluid phase, fundamentally changes just by adding more particles. So this is a study that we recently published in JFM. So at low mass loading, in this case the mass loading is 0.2, we have inertial particles in this Reynolds number 10,000 channel, and you get the classic shear production is balanced by viscous dissipation. And so this is production of TKE, and this is dissipation of TKE. You start adding more and more particles. These are heavy particles, and there's enhanced dissipation, and you actually see the TKE budget gets completely killed off, and you see a relaminarization. You add more particles, and they start to cluster, and you get into a cluster-induced turbulence, where you have a new mechanism, what we call drag production, that's proportional to the mass loading and the slip velocity, mean slip velocity between the phases, and you have a drag exchange term. So in this case, the flow is going left to right, and gravity is going this way, I think. So yeah, gravity is either this way or this way. I don't remember, but. In this, the gravity is helping induce a mean velocity difference between the phases, which is very important here. We're not claiming drag reduction here, because as we add more particles, we're forcing the mass flow rate to be constant. But the main idea is the turbulence is fundamentally changing, even though the Reynolds number stays the same, because of these different multiphase flow regimes. So if we want a predictive turbulence model, we need to account for that. RANDS today doesn't. Second example, I've started looking at heat transfer, trying to quantify the effect clustering has. So this is showing cold particles sedimenting through a hot gas. We could quantify the non-dimensional temperature as a function of time. And you can see that if this was a uniform distribution of particles, the heat transfer between the phases would occur much faster than if you had clusters, because you've reduced contact between the phases, and you get these hot spots that persist in voids, and then the fluid cools relatively fast where the clusters are. We see a delay in heat transfer by about a factor of 4. And if you look at the local heat transfer coefficient, it varies by about 7 orders of magnitude depending on where you are in the flow. So if you start thinking about heat and mass transfer in the context of turbulence model, it only complicates things, and we need predictive models for the unclosed terms that arise. In this case, this correlation between volume fraction and non-dimensional temperature is entirely responsible for the effect of clusters on this. And so this is just to motivate that we need to account for these non-trivial effects in order to have predictive turbulence models. And so the objective of this talk, develop accurate and predictive multi-phase turbulence models that capture relevant physics across scales. The first part of the talk will show how do we generate trusted data using highly resolved numerical simulations. We'll consider homogeneous sedimenting flows, so fully developed cluster-induced turbulence, and show some of the shortcomings of using existing turbulence models. And then look at new approaches to inform the unclosed terms. And so the first part of the talk will motivate really what we're starting to look at later on. So we're considering cluster-induced turbulence. Particles initially randomly distributed in the flow, and the flow is quiescent. They start to fall under gravity. There's strong coupling between the phases, and eventually it reaches a fully developed state. I would argue this is actually probably one of the simplest coupled, two-way coupled flows. In the absence of particles, you don't have any turbulence. There's no walls, and it's statistically stationary. But even for this very, very simple example, it's extremely difficult to model using existing methods because existing turbulence models in the context of RANDs doesn't account for two-way coupling. And so although I'd argue this is a simple two-way coupled flow, it's still very complicated and isolates the key challenges for turbulence modeling. And so in order to generate the data, we're using an Euler-Lagrange framework, NGA. So it's a second-order finite volume code. And so the usual Newton's second law for each particle. We have gravity, collisions using a soft sphere approach, and then the phases are coupled through drag that accounts for volume fraction Reynolds number. And we're generating several cases. In this case, we're considering 2D because we just started this 6 months ago and we're testing methods. But also, we do want to generate a lot of data. So we're varying both the Reynolds number the particle Reynolds number from 0.1 to 1, varying the mean volume fraction from 0.1% to 10%. And you can see that the flow, at least the level of clustering changes and the underlying turbulence changes. And so if you were to perform a averaging of the mesoscale equations, you would arrive at a set of coupled Reynolds stress equations that have a lot of unclosed terms. So I'm not going to show every equation, but if we just look at the fluid phase Reynolds stress, this is in the gravity direction, we have a number of terms. And so here what I refer to as phase averaging is essentially a Favre average on the volume fraction. And then the local velocity, the variation by its phase average is denoted here with the triple prime. So this is average on the fluid volume fraction. And so this is our fluid phase Reynolds stress. We have a pressure strain term and viscous dissipation. This is present in single phase flows. Pressure strain produces TKE in the horizontal direction due to reorientation. Viscous dissipation dissipates the TK to heat. And so here sigma is the viscous stress tensor. Drag production is the key production term in the absence of mean shear. So in this case, there's no walls as opposed to the channel flow where we had mean gradients. So here, all of the production in turbulent kinetic energy is proportional to the mass loading. And then this drift velocity here. So this is the fluid phase velocity fluctuation that's been averaged at the particle location. So it's sometimes termed the fluid velocity seen by the particles. It's essentially the drift velocity. So if the volume fraction and the fluid velocity is not correlated, i.e. there's no clusters, then this is 0 and we have no production of TKE. And then we have a drag exchange term. This represents correlations between fluid velocity and particle velocity fluctuations average at the particle scale. And then this is the fluid velocity fluctuations average with the particle volume fraction. And so these are terms that require closure. The pressure and viscous exchange are typically ignored because of the high density ratio. And so, as I mentioned before, pressure strain and viscous dissipation shows up in single phase turbulence. It's typically modeled using some type of Rota model. And so here this would be coefficient. And then it's a function of known values, the turbulent kinetic energy and the Reynolds stress that we solve for. Drag exchange, we've traditionally modeled in the past using correlation coefficients. And so we don't know how the, how the fluid velocity and particle velocity are correlated, and so instead we model this using a correlation coefficient. That's these betas that require to be modeled. And then the drag production is modeled using this constant here, which represents the ratio, the normalized drift velocity. So if we want a predictive turbulence model for this homogeneous case, then these are the type of terms that we need to close. And as I mentioned before, pressure and viscous exchange are usually neglected. What this is showing is I think it's an L infinity error between the terms that we could extract from the Euler-Lagrange simulations versus the models that I had just shown. Now those model parameters were tuned or determined for a 1% concentration and Reynolds number of 1. That's why you see smallest errors here. The challenge is if you look at different volume fractions or different Reynolds numbers, clearly these parameters, these coefficients vary strongly or depend strongly on those parameters. And so simply using extensions from single-phase models or single-phase turbulence models fails to be predictive. And we've spent the last couple of years looking at this, and it's been challenging, and that's been our motivation to move to a new technique. And so what my student asked and has been exploring is, closures adapted from single phase break down for even what I say the most simplified two-way coupled flows. Can machine learning provide accurate closure? Now, machine learning has emerged over the last couple of years in CFD for turbulence modeling, mainly for single-phase flows, but there's really been kind of two flavors, neural networks and sparse regression. Neural networks have the benefit of being completely general. It doesn't require any knowledge of the underlying physics, though I would actually lump this under a drawback. The drawback here is that it's difficult to express in compact form. What we're seeking is the functional form of these terms. We know that how the energy should be exchanged between the phases, and we want to make use of that, and we're trying to identify what those functional forms of those unclosed terms are. Sparse regression will give you that. It'll give you a compact algebraic form, and it provides model selection and regression. I'll explain what that means. But it does rely on the modeler to choose appropriate test functions to know, I think this should be a function of volume fraction or volume fraction squared or so forth. So this is the method that we're starting to look at. I'm not promoting any method over another. This is very preliminary work. It just, this is what we've been looking at and we've been seeing some success with. The idea with sparse identification or sparse regression, we define a model as y equals x times beta. And here y is the model that we desire, and x is a matrix of test functions that we need to supply. And so we generate some trusted data, in this case from our Euler-Lagrange simulations. And then we solve this optimization problem for beta, which attempts to minimize the error between the model and the known values. But then we also have this parameter lambda, which puts a penalty, in this case, on the L1 norm. What this tries to do is say, I want the fewest amount of terms. I don't want to have an exact perfect model, but it's really complicated with a lot of terms. I want to have a model that gives me really good results, but with as few terms as possible. We're also looking at L2, L infinity norms, and also penalizing the eigenvalues to give us a solution that remains stable. But in this case, we're just considering this one penalty. And so the idea here is we provide the data, and then it's an iterative process where we iterate on lambda, and we attempt to find beta such that it selects which test functions we use to give us this. Now, this has demonstrated success over the last couple of years for dynamic systems such as Lorentz attractors. But to my knowledge, it's never really been applied to realistic flows. And so we're just asking, can this technique be applied successfully to more realistic flows? And so the remainder of the talk, I'll first show some examples on single-phase homogeneous turbulence, and then apply it to one example of one of the unclosed terms that appears in CIT. So what we're doing here as this first test case is we're going to use a turbulence model to generate the data and see if we can, if this can return that model back to us. So we're considering homogeneous shear turbulence where we're prescribing the dissipation and the strain rate, and we're going to run many models of these. In this case, we're using the LRRIP model, so this is directly taken out of Steve Pope's book. And this is to generate our data. And what it does is it gives us our Reynolds stresses. We then use the known data in Y. This is produced from our trusted data. We populate it's kind of hard to see here, but this X matrix as a function of different combinations of things we might be important. So different combinations of Reynolds stresses and shear rates, they all have to have the units of 1 over time, and so that's one constraint. And then we adjust lambda and optimize to try to minimize this error norm here. And this is just to show you that the model we're using. So this rota constant's 1.8. C2 here is 3/5. The production term here is basically prescribed because we're prescribing the shear rate, and epsilon's prescribed. And what this shows is the Reynolds stresses produced by the model we gave it. And then this is what our sparse identification provides here. So it correctly zeroes out all of these terms, and it gives us essentially the exact rota model back. And so we generated the data with the rota model, and then this was able to identify that we had used that rota model. Found, so this is your negative 1.8 is your negative CR here. And so it worked well. So then the next thing we want to do is, well, let's do the same thing, prescribe the shear rate, but instead use direct numerical simulation. So here we're using DNS of homogeneous shear turbulence. We're considering 3 different shear rates. It's a fairly large simulation in order to generate our Reynolds stresses, and we're doing the same thing. This is just a matrix to show, this is basically what the algorithm gives you. So here are the different Reynolds stresses from that we predict. And these are the Reynolds stresses predicted by the turbulence model, the LRRIP. And what we see is that we do quite a bit better. I think there's errors shown. Well, the errors are on the next slide. But this is the LRRIP model here I showed before, and this is the model that the sparse regression predicts. And so you could see it's saying that we should include the off-diagonal Reynolds stresses. It's a little more complicated than the LRRIP model, but it gives you significantly less error. And so this is showing as a function of time the Reynolds stress, or this is the pressure strain term. And here the experiments are, the blue is the LRIP, that's the single phase turbulence model that exists. The black is the DNS, and the red is what the sparse regression predicted. So it was able to give us a better model, and it told us that we should include these terms in the model as well. So the final application will be going back to the cluster-induced turbulence example I showed before. So this was that the Reynolds stress equation when you average the mesoscale equations: pressure strain, viscous dissipation, drag exchange, drag production, pressure exchange, and viscous exchange. We'll just focus on term 1 for now. And so we know the exact expression. We can run our Euler-Lagrange simulations and compute this from the data. And this is what currently exists from the literature on how the rota model that exists for classically to close these types of terms. If we apply the sparse regression on it, we get something different. In this case, we have a weak dependence here on the Reynolds number and the volume fraction. And we're able to find something that gives us much smaller error. So this is the error you would get if you were to use a rota model with a tuned coefficient as a function of volume fraction and Reynolds number. And then this is the error that you'd get with this model. Now, in this case, our lambda became very small, so basically just was enslaved to the data. It gave us a model that exactly fits it, but it's somewhat complicated. And this does not ensure that your set of equations in the end is even stable. And so what we're looking at now is different ways to penalize this such that we can get maybe a cleaner functional form and something that remains, that ensures stability. So in the end, sparse identification is able to uncover complex dependencies on the flow. So it's showing how this pressure strain and viscous dissipation should be functions of volume fractions and Reynolds numbers and the different Reynolds stresses, for example, in order to improve the model accuracy. And so in conclusion, we were looking for accurate multiphase turbulence models. This is very much a preliminary work. Even the simplest two-way coupled flows, statistically homogeneous stationary, present many challenges. Sparse regression it allows you to get the functional form of the terms that appear in the average two-phase equations. But one thing we could ask is, if we train this on a certain set of data, does it remain robust and predictive outside the training set? What we've seen with the single-phase homogeneous shear turbulence is that it does work pretty well for the cases we considered, but obviously it needs to be tested more rigorously. As I mentioned too, we're looking at mixed penalties for increased model robustness. And then obviously applied to more complicated flows. We have a lot of data on channel flows. The physics is very non-trivial, and this might be a way to shed some light on how to close those terms. And with that, I think I probably went a little fast, but I'm happy to take any questions.